When large language models attempt deep, multi-step logical deductions, they often display a fatal fragility. A model can flawlessly execute 10 steps of reasoning, only to make a math error on the 11th, causing the entire logical structure to shatter. To understand why this happens, we have to look at how these systems are aligned. Modern AI model alignment relies almost entirely on sparse, human-provided feedback, typically a rating, a comparison, or a simple preference between two outputs. Long O. Yang and colleagues cemented this approach with InstructGPT, demonstrating that reinforcement learning from human feedback, or RLHF, optimizes global behavior toward helpfulness and safety. Today, this outcome-level ranking is heavily managed by direct preference optimization, developed by Rafael Rafaelov and colleagues, which streamlines the alignment process mathematically. But RLHF and DPO share a strict structural limitation. They are outcome evaluators. They score the final text the model produces, but they provide zero transparency into the internal reasoning that generated that text. They tell the model which output is better, but never why. Look at this diagram. As the cognitive complexity of a task increases, the reasoning string elongates. When the model eventually reaches an incorrect conclusion, it receives a single sparse score, like a reward of 0.1, applied entirely at the final node. From a learning perspective, a global negative reward creates the credit assignment problem. The model knows the final answer is wrong, but it cannot isolate the specific node where the logic collapsed. It queries the feedback signal to determine whether the error was factual, logical, or structural, and receives an empty return value. A system that cannot diagnose its own specific reasoning failures cannot scale to highly structured formal tasks, like complex mathematics or advanced coding, where a single misplaced variable breaks the entire execution. To solve this, the frontier of AI architecture is shifting toward dense, process-level supervision and generative feedback loops. Advancing past current cognitive ceilings requires models to calculate the exact location and cause of internal logical failing. Directed acyclic graph, where each node is a sequential logical step. Under standard RLHF, a validation signal appears only at the terminal 10th node. If a flaw occurs early, the global penalty washes backward indiscriminately. This indiscriminate gradient update actively penalizes the correct logical leaps that occurred before and after the error, severely degrading the model's overall reasoning efficiency. In high-level mathematical proofs or software compilation, a single syntax error invalidates the entire sequence. A model cannot improve if it is continually punished for the 90% of the logic it executed flawlessly. Sparse outcome rewards break down mathematically as the length of the reasoning chain increases, requiring a structural shift in how gradients are applied. The immediate mathematical solution to the credit assignment bottleneck is process supervision. In their paper, Let's Verify Step by Step, Hunter Lightman and his team documented the efficacy of process reward models, or PRMs. In this updated DAG, process reward models apply dense evaluation signals to every intermediate node. Nodes 1 and 2 receive positive validation marks, isolating the red rejection penalty entirely to node 3. The chain stops, mathematically resolving the credit assignment problem. Applying this step-level process supervision yields immediate, measurable performance improvements across structured, formal mathematical tasks. Yet, process reward models have a strict boundary. They provide scalar density, a binary correct or incorrect at each step, but they lack semantic density. Knowing exactly where a failure occurred optimizes the computational penalty, but it is insufficient for autonomous error correction. The model still lacks the actual vocabulary to process the nature of its mistake. Step-level supervision solves the mathematical assignment of blame, but fails to tell the model why the logic itself was flawed. To introduce semantic density, researchers are augmenting scalar signals with natural language feedback, replacing binary checks with explicit error descriptions. Work by Noah Shan and colleagues on reflection demonstrates how language agents use verbal reinforcement learning to evaluate their prior actions. Building on this, Aman Madan's self-refined framework trains models to iteratively critique and adjust their own outputs based on their own generative feedback. In our DAG model, the binary checks are now replaced by natural language text blocks. When an error is detected, the critique, like assumption X is independent, is routed back into the input context, forcing the model to iteratively adjust its reasoning for the next pass. Yuntao Bai's constitutional AI further proves that natural language principles can govern high-level global alignment, extending this semantic density beyond pure logic tasks. Transitioning to semantic density introduces a risk inherent to generative models. Wei et al.'s foundational chain of thought studies reveal a disconnect between the text a model generates and the actual computation occurring within its layers. This gap is known as the faithfulness trap, a state where the model's explanation diverges from its actual internal activation pathway. The model generates a smooth, logical-sounding explanation in text that contradicts the internal mechanism that produced the answer. Unconstrained generative critique accidentally reinforces this unfaithful logic. If a model evaluates its own reasoning, it trains itself to produce explanations that appear correct to human evaluators without actually improving its underlying computational accuracy. Generative feedback provides the essential vocabulary for reasoning, but without rigorous, sparse outcome verification to anchor it, it introduces severe hallucination risks. Because process-level supervision and generative critique contain inherent noise and bias, they cannot act as standalone replacements for standard reinforcement learning. Instead, the industry is building an augmented hybrid alignment stack. Here is a model of that unified architecture. The top layer remains the global scalar reward, utilizing DPO or RLHF to apply a final preference vector to the output. These sparse outcome signals remain the most efficient tools for guiding overall human alignment. But beneath that, a middle internal layer handles process validation and critique, utilizing dense DAG tracking and iterative text feedback. This internal layer solves the credit assignment problem, refining multi-step logic before the final answer. This architecture binds the layers together. Dense internal reasoning strictly filters upward into the global evaluation layer, acting as a hard constraint to prevent unfaithful hallucinations. This layered approach moves the focus of training from final outputs to the specific mechanics of the generation process. Training now targets the internal reasoning process, using critiques to identify and correct structural errors as they occur.